If your iPhone has a camera on the front and one on the back, why can it never show you what is directly behind your head? This feels like a simple question with an obvious answer, but the reality reveals a fundamental gap between consumer gadgets and true autonomous intelligence. We often assume that adding more lenses equals total awareness, yet geometry imposes hard limits that software cannot bypass. Today we unpack the mechanical story of why seeing everything requires far more than just stacking cameras on a slab of glass. The core issue is not about processing power or clever algorithms. It is about light itself and how it behaves in three-dimensional space. A smartphone camera captures a two-dimensional plane of light from its specific lens location. To see behind you, you need either a mirror system that reflects the rear view to the front sensor, or multiple cameras with overlapping fields of view stitched together in real time. Smartphones lack this because they are designed for retrospective documentation rather than continuous spatial awareness. As forensic analyses have shown regarding tracking data, these devices excel at logging past locations through GPS and Wi-Fi trails, but fail to provide the active high-frequency visual sensing required for seeing surroundings without physical obstruction. This distinction creates a massive engineering bottleneck known as self-calibration. True omnidirectional vision requires a system that knows exactly where every sensor sits relative to the others and how they move together. A phone's sensors are fixed, yet the user moves them randomly through space. Unlike an autonomous vehicle chassis which has rigid geometry known down to millimeters, a handheld device lacks a stable reference frame for what is behind you. Without this mechanical stability, stitching multiple camera views into a seamless 360-degree view becomes mathematically unstable in any moving context. The result is motion blur and parallax errors that would make navigation impossible if the system relied on them alone. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the difference between how sound and light map space to understand why robots need different hardware than phones. Research into acoustic localization proves that complex environments hide geometric data in echoes, allowing machines to theoretically map space through reflections of low-frequency waves. However, optical systems require direct line of sight or active reflection because visible light does not bend around corners like those sound waves do. While mathematics suggests one could hear a location through clever analysis of returning signals, the physics of vision demands that photons travel in straight lines unless reflected by a surface designed to capture them. A phone cannot mathematically reconstruct a behind view without external geometry or redundant sensors, because light simply does not bounce around corners like low-frequency sound waves do. This leads us to the critical difference between passive and active sensing technologies found in modern robotics. Forensic experts note that iPhone tracking is purely retrospective, logging historical data about where you have been rather than creating a live model of your current environment. In contrast, autonomous systems use active multi-sensor fusion combining LiDAR, cameras, and radar to create an instant 360-degree digital twin of the immediate surroundings. Adding more cameras to a phone does not solve this blind spot because it lacks the computational geometry and redundancy required for real-time elimination in a moving frame of reference. The technology exists to see everything, but the form factor is wrong for handheld devices where stability cannot be guaranteed. The stakes become clear when we look at safety-critical systems like autonomous vehicles or robot vacuums that must avoid obstacles without human intervention. If you understand this limitation, you realize why self-driving cars need LiDAR, which measures distance directly rather than relying solely on cameras to infer depth from stereo vision alone. A phone cannot see behind because it lacks the redundant geometry and calibration stability required to stitch a live view without errors that would cause a crash or collision in an autonomous system. The engineering reality is that true omnidirectional sensing requires a rigid chassis, precise sensor fusion algorithms, and often active emitting sensors like LiDAR units that measure time of flight directly. This explains why your phone remains just a camera, while robots become intelligent agents with spatial awareness. It highlights that autonomy is not about having more lenses, it is about the mechanical and computational architecture required to fuse those views into a coherent three-dimensional model of space. The shift from consumer electronics to machine intelligence demands a fundamental rethinking of how sensing hardware interacts with software logic. We are seeing this evolution in robot vacuums which use spinning LiDAR arrays, and in self-driving cars that integrate multiple sensor modalities to create redundancy against failure. Understanding why a phone cannot do it demystifies how robots actually perceive their world without relying on magic mirrors or speculative sci-fi technology. The path forward for robotics involves acknowledging these physical constraints rather than trying to brute force them with software updates alone. Future devices may eventually integrate flexible optics or distributed sensor networks that overcome the limitations of rigid lenses, but today's reality is defined by the physics of light and the geometry of motion. We must separate the hype about artificial general intelligence from the hard engineering work required to make machines see as well as they think. The blind spot behind your head remains a geometric fact until we build systems with the same stability and redundancy found in autonomous vehicles today. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.